Hello, scholars. We are going to do a review video for Unit 7 so that you can be ready for your celebration of knowledge. Quick expectations, make sure you're taking notes on this. You can focus better when you're actually thinking about what's important enough to write down as opposed to just kind of watching. Think about what standards you'll need to review more, because this should not be the only studying you do. It's a normal expectation for you to do studying outside of class. And make sure to come into office hours with questions so that you're getting the help you need. Okay, you can check homework too. We've got 3 standards, I guess 4, because there is a literacy piece this time, which you can bump up your Unit 5 literacy if you do better on. Okay, standard A says students can explain what a reaction rate is and what equilibrium is, chemical equilibrium. 7B can cause a chemical reaction to speed up or slow down through changing concentration, temperature, surface area, and catalysts. And technically agitation is part of this too, but it's a much simpler piece than these other 4. Part C, students can refine the design of a chemical system by specifying a change in conditions, so a stress, that would produce increased amounts of products at equilibrium. So this is basically Le Chatelier's principle, Le Chatelier. Okay, and then the literacy piece. Okay, so let's look at this first piece, standard A, and I'm just going to define reaction rate is how fast a reaction uses reactant and makes product. Now this is for forward reaction rate. Reverse would be the opposite. Alright, you might see some modeling for this, so don't be surprised. Like if we have a graph of time and we have a reaction like A goes to B, and this is the concentration of A, it should go down, right? And then if it were B, it would go up. Okay, that's for the forward reaction, of course. Reverse would be the opposite. Or you could see something like this, where it gives you, here's a certain amount of A and B, and then what happens when it reacts? Well, the A is going to turn into B, so if it goes all the way, you should be left with all B's. And then it gets a little more complicated when you've got coefficients involved, but it's really just reading the reaction, and you should be okay. Alright, and you also need to know what chemical equilibrium is. So here, I'll start a new one for that. Look at definition. Chemical equilibrium is when... You know what, let's break this down. There's really 2 things that you need to know. Okay, number 1 is the concentration or amount of reactant and product remains constant. And 2, because the rates of the forward and reverse reactions are equal. Okay, so constant, I want to be clear, constant, not necessarily, I think that's spelled wrong, equal. So you don't have to have, 5 reactants and 5 products. You just need to have a constant amount. Okay, so let's take an example like A goes to B plus C, and this has to be double-sided. If it's only a single arrow forward, you can't have forward and reverse be equal, so that wouldn't work. Okay, and let's just take a system. Now, just because the reaction is written as a left and right side, it's all in the same thing. So let's say this is occurring in water, and we've got, 2 of each. Just make things simple. Okay, now if this is truly an equilibrium system, then that means whenever an A creates B and C, a B and C is going back to form an A at the same exact speed. And so what do you notice? Well, you've got 2 A's, 2 B's, and 2 C's, even though both are still reacting. So this is chemical equilibrium. Okay, constant amounts because the rates are equal. Okay, let's look at standard B. So standard B is how can you speed up or slow down those rates? Okay, so there's 5, I guess, factors. 5 factors that affect rate. Okay, the most obvious is concentration. Then we've got temperature, that's a big one. Surface area, agitation, and catalysts. Okay, for any of these to make sense explaining, you need to understand that in order for a reaction to occur, 3 things need to happen. 1, the reactants, if it's a forward reaction, products, if it's going reverse, the reactants must collide. They must have enough energy, which they have to get over the activation energy. I'll move that in a second. And they must have the right orientation. If all 3 of these don't happen, then a reaction won't occur, right? So if we have A plus B goes to C, and we have our A and our B, and maybe the A is shaped funny. Maybe it's shaped like that or something, okay? And if we take these and we bump them into each other, boop, 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 they collide, yeah. I mean, you can see how they wouldn't do anything if they don't even hit each other. Like, you can imagine if there's a separation here and this B, there's no way for it to get over there, then they're not going to react. Okay, but if they collide, they're not going to react unless they collide in the right space, so maybe it has to hit here. Okay, that's the orientation piece. They have to have the right orientation. But they also have enough energy. You can imagine it's kind of like if you're trying to hammer a nail. You know, like you're trying. Here's a nail. Okay, and you hit it into where you want it to hit. But if you don't hit it hard enough, then it's not going to go anywhere, right? So you need enough energy. Yeah, so you need those 3 things. Okay. So concentration. Let's make sure we know what all these are. So concentration is how much per volume. That's horrible handwriting. So if we have 2 containers like this, and this one has like this many, it's a pretty high concentration. They're all crammed together. This one only has like this. It's a pretty low concentration. So this is low concentration. This is high concentration. And so you can see how the high concentration is going to have more collisions. It's not really going to change the activation energy, but it is going to have more collisions, and so this would speed up the rate, whereas low concentration would have a low rate of reaction. Temperature is a double whammy. So temperature makes the particles go faster, right? So and so they're going to collide more. But they also have more kinetic energy, because temperature is average kinetic energy, and so they overcome the activation energy more easily. And activation energy, a lot of times we'll use E sub A. All right, what about number 3, surface area? So surface area is how much is showing on the surface. So the 2-dimensional equivalent is like perimeter, so I'm not going to attempt to draw 3-dimensional figures for you. But let's say we have about the same amount, except this one is broken up into pieces. Looks like a face. Okay, if you put this together, they're about the same amount. But this one has more showing, so you can imagine, you know, if this is a particle of B coming in and the blue is A, not only can it hit the outside, like it can here, but I could also get in here and hit the inside. So again, we're going to have more collisions. Make sure whenever you're explaining any of these that you clearly demonstrate you understand what surface area is, or what temperature is, or what concentration is. Don't just say, oh, higher concentration, more collisions, right? Demonstrate that you understand it means there's more per volume. Okay, what about agitation? So agitation is when you stir something. So stir, does it look like it's stirring? No, it just looks like, I don't know, a magnifying glass or something. Okay, and this literally, I mean, there's really no other way to explain it. I mean, if you have these particles here and you're forcing them to move around, then they're going to collide more often. Okay, what about the last one, catalysts? Okay, it's probably easier to explain this by looking at a reaction energy diagram. So, reaction energy diagram we know from Unit 6, at least in theory. It's potential energy versus reaction progress. It starts with the reactants. And let's say this is exothermic, which means it's going to lose energy. The products have less energy than the reactants. And every reaction has to have some energy put in first. So the difference in energy is what we studied as the delta H. So this one loses a certain energy, that's why the delta H is negative. This is all review, I don't even know what I'm telling you. The energy that has to be put in to get it to the activated complex here, which is where the reactants all combine. It's a temporary molecule. I think you can read about this on page 2, the activated complex anyway. It's not really an emphasis in this unit, but if you're interested. This is the activation energy. Okay, and so if this is high, it makes it really hard for a reaction to happen. So what you can do is you can add a catalyst. Well, a catalyst is a chemical. Let me label my axes. Okay, a catalyst is a chemical which will lower the activation energy. Technically it does this by using a different pathway. So it would actually look something maybe like this, where there's actually separate reactions that are happening, but the point is, I mean, okay, I'm just going to erase that. That's probably confusing you. The point is that the amount of energy you have to put in to get it to the activated complex is lower to go from reactants to products. The delta H is the same. This hasn't really changed, but the energy that you have to put in right here is lower. Okay? I'll change that to black in case some of you can't see green. Alright, so let's look at the last one in our last 2 minutes here. Equilibrium. We already defined it, so now we're going to look at Le Chatelier's principle. So I have this set up. It says, explain and model how a decrease in pressure would affect the following system. Well, we know that Le Chatelier's principle says the system will do the opposite. Notice it's a double arrow, so it is equilibrium system. So if you decrease the pressure, here we'll just write it out. If you decrease the pressure, the system will counteract that change by doing the opposite and shifting to the side. So how would you increase the pressure, right? That's the opposite. Well, you increase the pressure to the side that has more particles of gas, with more particles of gas, which in this case, the A is aqueous, that's not even a gas. You have 1 here, and you have 2 here, so it'd be the products. In this case, the products have 2 particles of gas, and the reactants have 1. So, this could be a potential system, right? One of the A goes away, right? One of these reacts, and one of the B reacts, and you form 2 C's. So you can see I had 4 C's, now I have 6. I only have 3 B's now, and I have 3 A's. All right, so it counteracted the change. And you can see how, you know, if these are colliding around and causing a certain pressure, if you decrease the pressure, see I'm expanding the container, that's how you decrease pressure. All right, that's how that would work. All right, so that's it in a nutshell. This one takes a lot more practice. There's practice in the notes and the homework. Come to office hours if you need some help, and I'm sure you're going to do great. You are beautiful, intelligent, hardworking people.